This video was sponsored by Brilliant. Transistors are very simple by themselves, but combining them result in very powerful components, like arithmetic logic units capable of doing math, and latches, capable of retaining information to create memory. In today's video, we are going to use these components to create our own CPU. So we'll finally understand how a piece of silicon run programs. Hi friends, my name is George, and this is Core Dumped. Before starting, a quick reminder you can find me on social media. Also, I'll leave a question by the end of the video. I'll be giving away that one card everyone's been asking for, to the best answer. Previously, we learned about registers. We discussed that a register is a set of tiny memory cells called latches, made out of logic gates and interconnected in a way that retains information. Each latch in the register has its own output wire, which we use to read the value held in the latch. Registers also have input wires and a write enable wire to overwrite the values in the latches. When the write enable signal is off, the stored values do not change regardless of the input values. Activating the write enable signal is the only way to overwrite the values in the latches. Once set, the inputs can be deactivated, and the new values will remain stored. Our first goal is to reduce the number of wires used. We can modify each latch so that the same wires serve as both inputs and outputs. By activating a read enable signal, these wires act as outputs, allowing us to read the stored information. By activating the write enable signal, we use the same wires as inputs to overwrite the information in the register. This approach reduces the number of wires needed when working with multiple registers by combining their data lines into a single general data bus. When using this data bus as an input, the input value reaches each register. Since each register has its own write enable signal, we can activate the write enable signal of only the specific register we want to modify. The same principle applies to reading. Activating the read enable signal for the particular register we want to read from causes the general data bus to act as an output. By selecting the correct write or read enable input, we can read from or write to any register using a single data bus. Fortunately, we already know about the binary decoder, which can electronically select between multiple options. Now, let's talk a bit about memory. In the previous episode, we defined memory as an array of bytes. Each byte can be selected by inputting its position in the array through an address bus. A data bus, alongside a read enable input, can be used to read the value stored in the selected byte. This same data bus can also be used as an input, alongside a write enable input, to overwrite the value of the byte at the provided address. Our goal in this part of the video is to understand how instructions like load and store are executed at the hardware level. If you are not familiar with assembly language, don't worry. I'll explain some of these instructions along the way. Let's begin with load instructions. Typically, program data resides in memory. However, to manipulate this data, it often needs to be loaded into registers first. Within the CPU, there's a set of registers available for this purpose. The current instruction indicates that we want the computer to load into register 1 the value stored in memory location 1101. Essentially, a load instruction copies the value stored in a specific memory location into the designated register. While this process might seem straightforward in animation, this video is about understanding the hardware implementation involving cables and logic components to make this possible. Let's get to it. We'll start by connecting the memory data bus to each register. Suppose this is the instruction we need to execute. Since we aim to copy data from memory to a register, we start by reading the memory address where the data resides. This is accomplished using the address bus and activating the read enable signal of the RAM. Consequently, the memory data bus outputs the value stored at the provided address, making this value to serve as input to every register. Since we want this value to be copied only into register 2, we activate the write enable signal only for that specific register, making it overwrite its current value with the data we are reading from memory. On the other hand, with a store instruction, we perform the opposite action. For example, this instruction directs the computer to store the current value held in register 1 into memory location 0110. So now instead of reading from a memory location, we need to read from a register, in this case, register 1. Activating the respective read enable input causes the value stored in that register to become the input on the memory data bus. Additionally, we must specify the memory address where we want to store the value. Since our objective is to write to memory, we activate the memory write enable signal. And just like that, we've successfully copied a value from a register to memory. Quite straightforward, isn't it? Well, yes. But now we got the question. Where do all the signals necessary to control these components come from? We already established that binary decoders can be used for this task. But then where do the inputs for those decoders come from? The answer, after a quick message from Brilliant. One thing many of you agree on is that traditional studying can be boring. Fortunately, with Brilliant, learning new things and developing new skills doesn't have to mean endlessly reading PDFs. With Brilliant, you can learn a bit each day through their intuitive teaching methods. Every course on Brilliant is designed for learning by doing, not just reading. You can choose from numerous lessons in various areas of science, like math, statistics, and computer science. One of the best courses available now is on how large language models work. You'll learn the fundamentals of this incredible technology that's currently changing the world. Not only that, but you'll also get hands-on with real language models and learn about the importance of training data so you can tune your own LLM. You can sign up for 1 month of Brilliant Premium for free and get a 20% discount when subscribing by accessing brilliant.org/coredumped or using the link in the description below. Now let's answer, where do the input signals for these components come from? The short answer is from the instructions themselves. As discussed in a previous video, assembly language serves as a human-friendly representation of code that computers can understand. When we write assembly, an assembler, a specialized compiler, translates this human-readable code into binary machine code. This sequence of bits contains all the essential information to instruct the computer. For example, in a previous video we established that if the first 2 bits are 0, 0, the computer interprets the instruction as an arithmetic operation. In that particular case, the 3rd and 4th bits specify the type of operation. If the first 2 bits are not 0, 0, the instruction signifies something other than an arithmetic operation. For example, it could be a load instruction if the first bits are 0, 1, or a store instruction if they are 1, 0. In this design, for load or store instructions, the 3rd and 4th bits of the instruction don't indicate an operation code, but rather which register to read from or write to, and the last 4 bits represent the memory address. To distinguish between different kind of instructions, we employ a binary decoder. And the 3rd and 4th bits of the instruction serve as inputs for these other decoders, so they can activate the enable signals of the desired register. However, in this configuration, both the read and write enable signals of the register are activated simultaneously, yet only one of them should be activated depending on the instruction. Since we've already designated a decoder to differentiate between different instruction types, we can use the outputs of that decoder to ensure that only the desired input is activated according to the instruction. This allows us not only to select a specific register but also to activate either its write or its read enable signal, but not both at the same time. Moreover, if these 2 bits are not meant to interact with any register, such as in the case of another type of instruction, this setup prevents any signal from reaching the registers, thus keeping their stored values safe. Now, considering that the last 4 bits of the instruction represent the memory address we need to read from, in the case of a load instruction, these bits will serve as input to the address bus. Finally, to copy the value of the selected address to the selected register, we simply activate the memory read enable signal. This action allows the data bus to output the value, sending it to the registers. Since only the write enable signal of register 0 is active, only that register will overwrite its content with the received value. Let's do the same, but now with the store instruction. As we already know, this instruction copies the value from a register to a specific memory location. Therefore, the decoder should activate only the read-enable signal of the register specified in the 3rd and 4th bit of the instruction. In this case, the read-enable signal of register 2. This action makes the value of that register act as an input on the memory data bus. It's worth noting that the same wire that activated the memory read-enable signal in the previous load instruction is now deactivating it, which is precisely what we want. In a store instruction, we aim to write to memory instead. The last 4 bits of the instruction indicate where we want to write the value being inputted into the data bus, and to prompt memory to write that value into that location, the write enable signal of the memory should be activated. We achieve this by connecting the input to the corresponding output of the instruction decoder. And that's it. The value in register 2 is now copied to memory location 1111. Now we already know that the input of all of these components comes from the instruction itself, but how exactly? Well, before executing an instruction, the instruction itself needs to be loaded into a special register, called the instruction register. The output data lines of this special register are used as input for the components that decode the instruction. I'll get back to this register in a few. Before, I need to clarify something. Some of you might have noticed that this part of the circuit can be improved. Since both load and store instructions use the third and fourth bits to indicate the register to write to or read from, we could use a single decoder to achieve the same result. There are two reasons I'm mentioning this. First, if I don't, someone in the comments will point out there's a better way to do it. Some have been arguing in the last few videos that modern hardware handles this in better ways. Once again, my response is, here we're focusing on the fundamentals, not the fastest or most modern methods. Second, discussing these design decisions is when we start talking about architecture. Now, this term can be ambiguous, but let's focus on logical design for now. Different architectural designs can achieve the same result given the same instruction. From one perspective, we could say they are compatible architectures. But if we focus only on the instructions and their effects on the circuit, we could argue they are the same architecture. This is not always the case. For example, consider two similar architectures where the only difference is the interconnections of the instruction register outputs in the second one. This apparently trivial change causes both architectures to perform completely different actions. While in the first architecture, the sequence of bits in the instruction register means store the current value of register 2 in memory location 15. In the second architecture, the same sequence of bits means load into register 1 the value stored in memory location 15. Thus, despite appearances, the architectures are incompatible. If you've ever wondered why a program compiled for Intel x86 machines cannot run on a Mac or Raspberry Pi with ARM chips, even though all are computers that understand ones and zeros, well, that's the reason. While the executable file is a list of instructions the Intel CPU can follow, that same file is a meaningless sequence of ones and zeros that other architectures just can't understand. Let's continue with the main topic. We were talking about the instruction register, but before understanding how it works, let's see how our architecture executes arithmetic operations. We'll omit unnecessary components for simplicity. As described earlier, the first two bits being 00 indicate an arithmetic operation. To perform this, we'll use the arithmetic logic unit we developed in the first episode of this series. If the instruction is an arithmetic operation, the third and fourth bits specify the type of operation, in this case, subtraction. These two bits will serve as the opcode input for the ALU. The ALU needs two values to operate, so we need to read from two registers simultaneously, accessing each register's data line directly. This requires internal logic to bypass the general data bus used previously. The fifth and sixth bits of the instruction determine the first operand, while the seventh and eighth bits determine the second operand. But we can't connect the registers directly to the ALU because its inputs could be any of the registers. We need circuitry that allows us to select which signals to send. This is achieved by using a multiplexer, which internally employs a binary decoder to select which input bus value is sent to the output bus. Now, to simplify the diagram, I'll assign a color to each register and draw its respective data bus in that color. We can use two multiplexers, one for each input of the ALU. The inputs of these multiplexers will be the individual data buses of each register. The output of the instruction decoder, which identifies arithmetic operations, can toggle the read-enable signal of all the registers, making them output their values through their respective data buses to serve as inputs to the multiplexers. We then need to instruct each multiplexer on which register values to pass to the ALU. In this case, 205 and 53. Since this is a subtraction operation, the ALU will output the difference between the input values, which in this particular example is 152. The result of the operation needs to be stored somewhere. In many architectures, it is stored in one of the registers that contained the operands. In our architecture, the result of any operation is stored in the register that contained the first operand. But we can't write to it directly while reading from it. Instead, the result is temporarily saved in a register. Then, the registers are connected and set, so the value can be written to the target register, which, in this case, is register 1. At this point, you've probably noticed that as we progress in this video, I'm starting to abstract more concepts and omit some details. This is intentional. I've done my best to provide a clear explanation. Unfortunately, I don't have enough screen space to draw every decoder, logic gate, multiplexer, or other component necessary to execute each possible instruction. 15 minutes wouldn't be enough either. Hopefully, the overview of how the load and store instructions are decoded and executed gives you a brief idea of how this component, which we will call the control unit, works under the hood to decode a whole bunch of other instructions. Now let's explain how the control unit works. This is when we revisit the pending explanation about how instructions are loaded into the instruction register. This is perhaps the most important part of this video, so pay attention because what I'm about to explain is practically how CPUs run programs. The main job of the control unit is to read each instruction of a program and send the necessary signals to all other components to execute each particular instruction. In a way, the control unit acts like an orchestrator. Inside the control unit, there are special registers, such as the instruction register and the address register. Additionally, there are small 1-bit registers called flags, which will be very important in the next episode. All of these components are packed inside another component known as the central processing unit, also known as the CPU. When this giant circuit is powered on, everything is set to 0, so both data and instructions need to be fetched from an external source, memory. Unlike the general-purpose registers, the registers inside the control unit each have a specific purpose. We already know the purpose of the instruction register. The address register's purpose is to point to the memory location of the next instruction the CPU will execute. Currently, that location is 0. To load the instruction into the instruction register, the control unit activates the memory read-enable input, so the memory can output the value stored at the provided address. In our architecture, this value is sent to multiple registers, so the control unit must activate the write-enable input of the instruction register. This process of bringing instructions from memory to the CPU is known as the fetch stage. Then comes the decode stage. The outputs of the instruction register are inputs for all the internal components of the control unit. In this step, the internal circuitry reads and interprets the bit sequence in the instruction register in order to send the necessary signals to all components needed to execute that specific instruction. And once everything is set up, the CPU can execute the instruction. In this example, copying the value from memory location 14 to register 0. This is known as the execute stage. And just like that, our CPU has run the first instruction of the program. After executing the instruction, the internal circuitry of the control unit increments the value of the address register. In our architecture, the value is increased by 1 because each instruction is 1 byte long. Modern architectures have thousands of possible instructions, so instructions are much larger, and the increment value can vary. This increment operation ensures that when the CPU goes back to the fetch step, the address register points to the next instruction of the program. And the cycle repeats. The instruction is loaded into the instruction register, decoded, and then executed, here, copying the value in memory location 15 into register 1. Afterward, the address register is incremented, pointing to the third instruction during the following fetch stage. This time, the instruction is an arithmetic operation, specifically, an addition between the values in registers 0 and 1, which were loaded in the previous 2 instructions. The control unit must activate the read-enable signal of both registers and use internal multiplexers to direct both values to the ALU inputs. The ALU also needs the opcode for the addition operation. The ALU then outputs the result of adding the 2 numbers. And as we learned earlier, the result is temporarily stored in an internal register, giving the control unit time to reset and set the signals needed to store the value in the specified general-purpose register, which in this case is register 0. After executing the instruction, the address register is incremented, and the cycle repeats. Since this is a store instruction, the control unit needs to set everything to copy the value from register 0, where the result of the addition is held, to memory location 13. And there we go. We've come all the way from transistors to creating our own tiny CPU that run programs. If you think about it, the program we just ran is exactly what a line of code like this would look like when compiled for our tiny architecture. We load 2 values, add them, and then store the result in a variable. In this example, location 13 is where the content of variable A will reside in memory. Finally, for the people with more experience, I didn't mention the concept of a clock because it would make this video more complicated. I'll talk about clocks in a future episode. For now, I'll leave you with the question I mentioned at the beginning of the video. And that about wraps for now. In the next video, I'll talk about how CPUs run more complex algorithms, like conditions and loops. So don't forget to subscribe because you don't want to miss it. And if you enjoyed this video or learned something, please hit that like button. It is free, and that helped me a lot. See you in the next one.